Hello, in this video we're going to expose the secrets of high performance drones and more specifically the larger payload carrying hovering drones. We will explore if scaling up the drone has any benefits. How can we get drones with long endurance? How can we increase the payload? Are there any recent breakthroughs in drone technology? These are all the questions that we will probe in this video, so do watch this till the end. We will limit ourselves with rotor-based drones, and fixed-wing drones will be covered in a separate video. Away from built environments, in rural settings, drones have started appearing in our skies. A decade ago, we were shown a vision that soon our packages and even takeaway food would be delivered by drones. Retail and marketplace companies had a keen interest in this because with delivery drones, they had an opportunity to reduce their last mile logistic cost. While drones have not occupied our city skylines, yet they certainly are seeing increasing applications outside of it. There are now drones for medical supplies, disaster relief, drones for crop dusting and seed spreading, drones for providing feed to fish, and even drones for sending munitions and supplies to the outpost and war fronts. The proving grounds for drones today are the rural areas. Performance here will pave way for urban cargo transport and urban air mobility in the future. In cities, they will not just be used for goods transport, but can also assist in emergencies like rescue, evacuation, and even firefighting. It is interesting to note that drones have already been developed that can go deep into the fire site, can release superfine dry powder, and can extinguish fires of up to 100 cubic meter at a time. In Africa, long-distance fixed-wing drones are already supplying blood and other essential medical supplies in remote areas in under an hour's time, where road transportation would take several hours. In large ranches of Australia, drones are helping farmers keep an eye on their livestock. So there is no question about the utility of these drones. Let's now look at their engineering and figure out what are the crucial aspects of their design which impact their performance the most. First, let's talk about scale. What happens if we take a drone that is well performing and scale it up, for example, the DJI drones? The topic is slightly confusing because we have noticed that several light and small toy drones that weigh less than 300 grams have a flight time of less than 5 minutes. On the other hand, we have some premium photography drones that weigh around 1 kilogram but have a much longer flight time. For example, the Evo 2 has a flight time of 40 minutes, the DJI Mini 3 has a flight time of 51 minutes, and the Potensic Dreamer has a flight time of 31 minutes. Does this mean that scaling up allows for a longer flight time? The answer is not that straightforward. Take for example the DJI Mini 3. Let's say we scale it up and double the size of it. Doubling the size means that the existing weight of the drone would increase by 8 times. This is because of the square cube law. That is, existing weight will increase from 249 grams to 1992 grams. The scaled up DJI drone would have space for not 2 but 8 battery units as the dimensions increase in all directions. At first glance, it might look that if the weight has increased by 8 times and 8 battery units are used, then the performance should remain the same. But if we dig deeper, then we find out that it is not the case. To do this, we'll have to examine how much the required power increases. Now, there is a very simple formula for calculating power. Note that calculation of power requires the area of the disk. As the size of the rotor blade doubles, the area swept by the propellers would increase by 4 times. This in turn would mean that the power required for the scaled up drone would increase by not 8 times, but by 11.13 times. This means that the flight time would drop from 51 minutes to 36.6 minutes for the scaled up drone. The Payload effect will also come into play. The Payload effect implies that if you drain the battery faster, you get less energy from it overall. So the flight time would in reality be even lower. What we have learned is that just simply scaling up a drone would not increase the flight time. It would in fact reduce it because the weight increase is higher than the disk area increase. So in order to maintain the same performance characteristic of a small drone in a larger drone, we must increase the propeller size by more than a linear increase, or more specifically by following the power law. The key parameter is the disk loading. It is the ratio of weight of the drone with the propeller area. As long as the disk loading is kept the same, scaling up will give similar performance. We have seen that for these high-performing drones, the disk loading is less than 7.5 kilograms per square meter. And for DJI Mini 3, the 51 minutes of flight time is because of very low disk loading of 3.41 kilograms per square meter. If you want to have multi-copter drones that can last over an hour from battery, then we will have to minimize not only the weight but also reduce the disk loading. We also need to increase the mass fraction of the battery, that is, increase the ratio of battery weight to the total weight of the aircraft. For the DJI Mini, the battery weight was nearly half the total weight of the drone. As for toy drones and why they mainly have poor performance, it is because despite the lower weight, they use lower quality batteries with less capacity and have a lower fraction of battery as a percentage of the weight of the aircraft. For example, a 27-gram battery in a 200-gram drone. The focus in toy drones is low cost and safety. Notice how with a simple mathematical principle, which is the square cube law, we were able to predict the drone's performance for a bigger scale. If you want to learn more about scientific principles, then I would recommend the platform Brilliant.org. Brilliant has courses on scientific thinking with application on topics like structures, flow, heat, light, and relativity. It improves your reasoning and enhances your analytical skills. There are thousands of lessons on Brilliant, from foundational and advanced maths to AI, data science, neural networks, and more. New topics are added every month. For the followers of this channel, Brilliant.org has an offer. For a full 30 days of free trial, just visit brilliant.org/electricaviation or click the link in the description. What's more is that the first 200 of you will get 20% off Brilliant's annual premium subscription. Do give it a try. Now let's move on to the more workhorse drone like the agriculture drones. These drones can carry a payload from 10 kilograms to 50 kilograms. The flight times are generally around 9 minutes. The first thing to notice about them is that instead of using coaxial rotors, they add more rotors. So most of these payload carrying drones are either hexacopter or octocopters. The disk loading of these drones is around 17 kilograms per square meter with the payload included. Another thing to note about them is that they all use lithium iron phosphate batteries or LiPo batteries. LiPo batteries aren't the best batteries within the lithium battery chemistry umbrella. They have an energy density of around 140 watt-hour per kilogram. This is less than half of the best performing lithium batteries, which have an energy density of 300 watt-hour per kilogram. The advantage of LiPo batteries is that they are safe and less temperature sensitive. In most cases, you don't require a cooling system around them. On the other hand, the batteries packing higher energy have to be maintained between a certain temperature band. A solution to this problem comes from vertical aerospace. The rotor downdraft is passed through the cooling fins. That in turn cools the cells. The batteries in large payload carrying drone weigh up to 35 kilograms, so there is room for using higher energy capacity batteries with a cooling system, and endurance can be increased. There's also room for optimizing the battery mass fraction. Let's now look at the breakthroughs in technology that increase the flight time of the drones from minutes to hours. Turns out there are a few. The first technology uses a gasoline generator instead of batteries. Using this technology, the Gaia 160 hybrid drone flew for 175 minutes and covered a record range of 100 kilometers. Its spec reveals a 7-liter tank for petrol, a generator that weighs 4 kilograms, and is able to generate 2000 watts of electricity. It also has a couple of 5000 milliamp hour batteries. The overall weight of the drone with the fuel is just 19.5 kilograms, and it can achieve a flight time of 4.5 hours. Even more impressive but expensive is a fuel cell solution. Through the use of fuel cells, a record flight time of 5 hours was achieved by the Helium X drone. Note that a fuel cell is more efficient than a generator and also results in just water vapor emissions. So this is also another solution that has the potential to produce both long endurance and high payload carrying drones. The most exciting development, however, has come from a project which wasn't trying to make a drone. It was in fact aiming to make a quiet and efficient personal electric helicopter to win the GoFly award. Note that GoFly is an initiative that has a prize money of $1 million and requires the design and build of a safe, quiet, ultra-compact, near-VTOL personal flying device capable of flying 20 miles while carrying a single person. One of the participating team, that is Team Harmony, decided that instead of using several rotors, a single large coaxial rotor would be used. This meant that for the same footprint, the disk area for their aircraft was 4.26 times higher. After thorough research and testing, Team Harmony developed the Araya rotor system, which was not just 18 decibels quieter than a comparable quadrotor drone system, but also consumed 55% less power. Needless to say, less than half of the amount of power required by the Araya rotor system would increase the flight time when used in any drone. In the past, a single large rotor system was overlooked by drone developers because to achieve 6 degrees of freedom during flight, the required system with a single rotor was mechanically complex. It required at least 3 actuators, a swash blade, and several linkages to change the pitch of the blades and the axis of rotation. On the other hand, the same 6 degrees of freedom could be achieved in a quadcopter just by changing the rotational speed of the motors independently. It is the mechanical complexity of a rotor hub that has discouraged the developers from pursuing single large rotors. But now there has been a recent development that can turn the tide. By using a simple teetering hinge and just 2 actuators, Paulus et al. Have simplified the rotor hub and have emulated the complete flight dynamics of a fully actuated micro-air vehicle. Developments like these will encourage drone makers to pursue single large rotor solutions which are much more efficient for hovering drones. An example of the efficiency a single large rotor system brings is demonstrated by a drone used by the military, the Black Hornet Nano. This tiny 16 centimeter drone, which weighs just 18 grams, has a single large rotor which allows it to hover for about 25 minutes. It is also for this long flight time for a drone of its size that a single unit of this tiny drone costs $195,000. Just for comparison, the large payload carrying drones on the other hand cost less than $15,000. So to reiterate, what we have learned in this video is that lowering the disk loading along with lowering the overall weight of the drone would yield longer endurance. To decrease the disk loading, larger rotors should be considered. Higher fraction of the total weight of the aircraft should consist of batteries, and the batteries used can be of higher energy density with cooling carried out by rotor downwash. And with this, the video is concluded. If you learned something from it, then please do give it a thumbs up. Thank you for your attention.